All right, welcome to today's session. We are in week 5 for Algebra 2, and we're starting a new unit on exponentials and logarithms. So if you're thinking, what in the world is a logarithm? We'll be learning about that this unit, but not today. Today we're really focused on exponentials. We'll get to logs later in the unit. But if you guys think about addition and subtraction, multiplication and division, they're opposites of each other, correct? So exponents and logs are also opposites of each other. So that's what we're going to be learning this unit. Even if you have the notes in front of you, the only part that is not copied down is the essential question. So this week, the essential question is going to work just a little bit differently. It says at the end of our session today, you'll be taking a quick quiz and putting your score into the Dropbox. So for those of you watching at home, I will give you the link to take that quiz at the end. Those of you that are here in person, you automatically get your full 10 points by signing in. So that's kind of what we're going to do today. So I will give you the website for your week 5 essential question a little bit later in the session. So unit 2 is actually unit 10 in your book. So I know that's kind of confusing when you guys are doing your homework. It's because it's a semester. When the semester stops and we start over, even though we're calling them unit 1, unit 2, unit 3, in our book we're halfway through our book at this point. So we are in unit 10 now, and today we're going to focus on 201 and 202. 203 will be next week. So here's kind of the big idea, and if you have your notes pre-printed out, there's a slide on this. This is showing you how to change from a radical to an exponent. So kind of take a peek at the characteristics here. You have your base inside the radical. Your base is kind of always your big number. You're going to have an exponent, and you're going to have an index. The index is the number that we call the one that's right in the little root area. That's called our index. So watch how it changes into exponential form. The exponent goes on top. The root goes on the bottom. And it really does make sense if you think about it. Where are exponents always located? Really high, right? That's your exponent. So exponents are going to be the one that's really high, and then your root is going to go underneath it. So we're going to practice going forwards and backwards. If I give it to you in this format, can you write it as an exponent? And if I give it to you as an exponent, can you write it as a root? So let's try a few together. You're going to see it's not as hard as it seems. So if I have the 4th root of 7. Right now this is radical form. How do I know it's radical form? Because you see a root. I need to write this in exponential form. So my base is 7, so I'm going to put the 7 over here. Now I'm going to make my fraction. There's 2 parts to my fraction. There's the top part and the bottom part. The top part we said is the exponent. The bottom part we said is the root. So I definitely see a root here. I see that that's going to be a 4. So let's all add the 4 in right there. But I don't really see an exponent this time. When we don't see an exponent, there really is something right there. What do you guys think? What number could I add there that's not going to change my problem at all?
1.
7 to the 1st power. Good job. Thank you, Billy. So really, that is what it would look like in exponential form. 7 to the 1 over 4. So going backwards, I know it has it over there for you on the left already, but we'd put it inside the root. The top would be the exponent, the bottom would be the root. So it's kind of just getting used to this new funky format. So on this same slide, I want you to add in one more. I want you to try this one. Ready? So everybody add this one in. The cubed root of x squared. So take that exponential radical notation and write it as an exponent. Write it as a fraction. So we said before it's going to be a fraction. My exponent will go on top. My root goes on the bottom. So my exponent this time is a 2, and my root is a 3. So we'd have x to the 2/3. Let me pause for just a second. Does anybody have a question on these first 2 examples? I know they're new, but they're not super difficult. Okay, let's try this one. I want us to take this one, And there really should, oh yeah, that has both parentheses, sorry. I was only seeing one at first. So how would you take this radical and write it as a fractional exponent? So you try for just a second. It's starting to look scary, but it's not scary. So the base is always what's underneath the radical. So my base is going to be x minus 3, and all of that is going to get raised to a fraction. Now I'm going to keep it in parentheses because that's showing that the whole entire thing is going to be raised to this fraction. So what are the two parts to my fraction? The top part is your exponent, the bottom part's your root. So everybody look up there. What exponent do you see? Everybody says? 5. Good job. Doesn't tell me a root. But what we learned in Algebra 2 is that even though it doesn't give me a number, there's really a number hidden there, right? So what kind of number is hidden in any root? What's really there? A 2. Good job. Because they're all called square roots. It's automatically a 2 unless it tells you otherwise. So my exponent goes on top, 5. My root goes on bottom, which was a 2. Good job. Any questions about that one? Okay, great. So try this one. I'm giving it to you in exponential form, and I'd like you to write it in radical form. Can you believe you have a whole test just on this, just going back and forth? That's it. So this first quiz for Unit 2 should be 100% from everybody. Okay, would anyone like to volunteer an answer out there? Okay, Billy?
5/4 and a square root and then 7.
Okay, so he's saying the 5 would be the base, the big one, and it's 5 to the 4th, because the 4 is the exponent. The bottom's my root, so I'm going to put a little 7 right there. Very good job. Okay, let's try one more. I'm adding this one onto the same slide, so I didn't make a slide for this one. I'm just having you practice. This one you can actually solve. Can you give me your final answer? After you rewrite it, you're going to see, oh, I can solve that one. I know how to do this one. So 64 is my base. My exponent's a 1. My root is a 2. So really what this is saying is, what's the square root of 64? And what would my answer be?
8.
8. Great job. So here's a trick. Anything to the half power, anything raised to the half power, really what are you doing to it? You're taking the square root of it. So if I say 100 to the 1/2, what would be your answer? 10. Because you're saying, what's the square root of 100? 81 to the 1/2. What's the square root? 9. Good job. So anytime you guys see the 1/2, what does 1/2 mean? Square root. Why does it mean square root again? Because the top number is my exponent, the bottom number is my root. So we're always talking about the second root, or the square root. Good job. You're going to see this one more than any other because they use it the most often. Okay, really good job. All right, we ready for a hard one? I think you guys are ready. Because it can't stay easy like that forever. So this one's already copied in your notes if you have your notes pre-printed. Before we try and tackle this one, I want to remind you guys of some of your exponential rules. So let's pretend I have, and you don't need to write this down, you can just watch. Let's pretend I have this to the 4th power. What do I do with my power that's on the very outside? What am I going to do with this 4? Who remembers? What do I do?
Multiply the, not sure, I can't remember what it's called, but you multiply the 4 by 2.
Good. So we're going to take the 4 and we're going to multiply it by both of my other exponents. So that would be x to the 2 times 4 would be 8, and my y would be 3 times 4, which would be 12. Everyone okay with how I did that? You nodding? Yes? Okay. So what am I going to do with the 1/4? I'm going to multiply it. What am I going to multiply it by? Every single exponent, every single piece of the puzzle, I'm going to multiply it by. I'm going to do these with you. So let's start with my 64. So for 64, I'm doing 1/2 times 1/4. Do we remember how to do a fraction times a fraction? You multiply straight across the top, straight across the bottom. So 1 times 1 would be a 1 on top. 2 times 4 would be an 8 on the bottom. So this will be 64 to the 1/8. How do we do so far? Okay, just multiply. Let's try my x's. So my x, it's 4, and 4 times 1/4. So how do I do a whole number times a fraction? Let me just put it in the corner in case you've forgotten. So 4 times 1/4. You can really put the 4 over 1. That way you're dealing with two fractions. Go straight across the top, straight across the bottom. So what would 4 divided by 4 be? 1. 1/4 of 4, 1. Good job. Now let's do my y. So I have y to the -2. So this time it's -2 times that 1/4. I'm also going to put that underneath a 1. Let's go straight across the top, straight across the bottom. And how is that going to change? If I have -2/4, how can I reduce that? -1/2. Just reducing. Good job. You guys are doing great. So I'm not quite done. It gave it to us in exponential form. I now want to write it in radical form. So we're going to take each piece of the puzzle one step at a time. So I'm going to highlight the piece I want us to focus on first. So can you please rewrite 64 to the 1/8 as something with a radical, please? So the 64 would go inside, the exponent's the 1, the index is an 8. So it would be the 8th root of 64. Everyone okay on that first step? The x is just to the first power. I don't do anything with whole numbers, right? Whole numbers are great. I don't have to do anything with them. So it's just going to say x. That was easy. Now I'm to my y. My y has a negative exponent. If we remember back, I know it's been a while, there's something I'm supposed to do with negative exponents. So I'm not able to write it right now with the square root form. I can't do that yet. I have to make it a positive exponent first. So anybody remember the rule about negative exponents? Like if I have this, if I just have x to the -3, how do I make that a positive? Good. It flips. So right now it would be considered in the top. So to make it a positive, it moves to the bottom and the exponent becomes positive. It just has to change sides of the equation to make it become a positive. So watch what I'm going to do to my y to the -1/2. So right now, if we pretend it's over 1, the y is on the top. Everybody agree with me? So where am I going to move it to? The bottom. So let's all move it down. It now becomes a positive. And I would love to circle it and say I'm done, but I'm missing one last piece of the puzzle. Do we know what the piece is? Why is this not fully simplified yet? I'll highlight it. Can't have fractional exponents. So I need to switch my fractional exponent into square root notation. So just like we did with the 64, we changed how it looked. I need to do the same thing with the y. So my final answer will be the 8th root of 64 times x on the outside. And then on the last slide, we learned a lot about the 1/2, right? 1/2 is always what? Just a square root. Good job. So this would be your final answer. Let's put a bubble around it. Give yourself a smiley face. You did a great, great job. Okay, so those are kind of the big ideas today. How do I deal with fractional exponents? What does it look like in square root notation? And simplify it as much as possible. So let me pause for a second. Does anybody have a question on any of those steps up there? All right, so let's try again, because we know the best way to practice is to practice. There's no shortcuts in math, unfortunately. I love Mr. Bremer, but I tell him all the time, history, okay, you can sort of get by in history with shortcuts. Math just doesn't work that way. You just have to practice and put in the time. So this time, if you notice, I have numbers on the top, I have numbers on the bottom, I have all kinds of variables going on. So let's see how we want to approach this problem. I like to deal with my whole numbers first. So when I'm going to write my new problem, I'm going to do my division bar, because you are going to have a top part of your problem and a bottom part of our problem, so it helps us keep track of what goes where. Let's start with my whole numbers. What's 16 divided by 8? 2. So do we see how that's just normal? Right, those are just normal constants out in front. 16 divided by 8, I have a 2. That part's simplified. Awesome. But now I have variables in the top, variables in the bottom. Like how do I get all the variables to be on one side? So let me remind you about our rules. If I have x3 divided by x, what that really means is x, 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 and x. You cross off what they have in common, and I'm left with 2. So what was the shortcut rule that we learned back from Algebra 1? And I know it's been a really long time. What do you do with your top and your bottom denominators? What do you think? How would I go from 3 and 1 and get 2? You're subtracting them. So it's always the top minus the bottom gives you your final answer. And if I write it all the way out, it's easy to see why the rule works. Now I have fractions. So it's really important that we do know the shortcut rule, which is subtraction. So let me hide all this, make some room for myself. So how am I going to do my top p minus my bottom p? My top p doesn't have a number, so I can add a 1 in there. Would everyone agree with that? Okay, so down here, let's write that we're working on my p's right now. So my top p is 1 minus my bottom p. What's the bottom p? 3/4. How do I do a 1 minus a fraction? Any ideas? Exactly. So I need to have common denominators in order to subtract my fractions. So instead of saying 1, hopefully we all know 1 is the same as 4/4. So 4/4 minus 3/4 gives me 1/4. So I'm going to have p to the 1/4. So I dealt with my p's. Now let's see what else I have going on. I have a q to the 1/3. There's no q's on the bottom, so let's just rewrite my q as q to the 1/3. But now I have this r to the -6 on the bottom. It's the only r that I see. I don't want negatives for sure. So how do I get rid of the negative? I have to flip it. So it's on the bottom right now. Does everybody agree with that? So where is it going to move to? The top. And when I move it to the top, it'll become a positive. Hey, that's handy. I ended up with nothing left on the bottom. So you could put a 1 there, or you don't even have to write the bottom anymore, correct? Everyone okay with that? So your last step, you guys, let me give you a minute to work on it. I want you to change exponential notation and write it in radical notation. So the 2 stays the 2. Everyone okay with that? Because there's no exponent on it, right? 2 stays the 2. So I want you to try the 1/4 and the 1/3. Okay, so the 2 stayed the 2. Let's move on to the p to the 1/4. So the p would go inside. Your exponent's a 1. Your root is a 4. For the q, your exponent's a 1. The root's a 3. How about R6? What do I do with R6? What do we think? Is it a fraction? No. So it just gets to stay. Nothing happens to it. It's just an exponent. So here's kind of the cool thing to remember. If it's a fraction, the top's the exponent, bottom's the root. If it's not a fraction, it's just the exponent. Because really think about it. If I were to make this a fraction, what number would be on the bottom? A 1, right? It's just like 6 over 1. So this number is always your exponent. Let's simplify this one last time because on a test or a quiz, they would not write those 1s in there. So your final answer would be 2 4th root of p, 3rd root of q, r6. The math is not the tricky part. It's understanding the process and what exponents need to move, all of those things. I mean, the trickiest math was 4/4 minus 3/4. That was the hardest math going on the page. It's just checking to see if you guys recognize the pattern and you know what to do with your negative exponents and you know what to do with fractional exponents. So it just takes practice. Okay, here we go. So anytime they give you guys numbers, do you guys see how there's no variables this time? They want you to solve this, meaning solve it all the way until you get a numerical answer. But I'm going to teach you a trick today, a hint. It's not really a trick. It's a mathematical process. Let's rewrite this first as an exponent. You're going to see why in just a minute. So first, let's rewrite this in exponential notation. And keep in mind that the word is really telling you what you're doing, because if I say exponential, you're talking exponents, right? That's really what's going on. So it's not such a crazy word. So this is really 80 to the what? What's my fraction? What over what? Okay, good. So 3 over 12 first. But then, what we were told in class here, somebody mentioned we can reduce the 3 over 12 and it can become 1/4. Oh, that's going to be much nicer to work on. A much nicer problem. Because think about what this is saying. 80 to the third means 80 times 80 times 80. That would be a huge number. Then you're looking for what number times itself 12 times can be pulled out of that radical. That's a long problem. This is a much shorter problem.
So you
So,
can divide the outside number by
opposite. It's the inside number divided by the outside number. So it's always your exponent divided by your root. So it's going to reduce to 1/4. So we're still going to solve the problem. So we need to put this back in the exponential form now. Back into radical form, sorry. So this would be 80, 4th root of 80. If you are able to go straight from radical to reducing the radical, that's fine. But a lot of students have to see it as a fraction to be able to reduce it. So that's why I'm just showing you. If you need to write it back this way and reduce to the 1/4, that's fine. If you can do 3 over 12 and reduce to the 4 without doing that step, that's fine. So what I'm looking for here is what is the 4th root of 80? So what we learned how to do is I have to break this down into its prime factors using factor trees. This was last semester. I know it's been a while. So we're going to do it together. And I'm looking for something that goes into 80 4 times. Like, is it 2 times 2 times 2 times 2? Is that 80? Is 3 times 3 times 3 times 3 80? You know, what number 4 times is 80? So let's do a factor tree here. I think we learned factor trees in 8th grade. So what times what is 80? Doesn't matter where we start. We're all going to get to the same final answer. So I'm going to say 8 times 10. Both of them are not done breaking down yet. So 10 is 2 and 5. 8 is 4 and 2. And 4 is 2 and 2. So notice I take my factors all the way down until I hit prime numbers. Once I hit a prime number, I circled it to let myself know that I was finished. So any questions on my factor tree? Do we all get the same factors? Even if you started with 2 times 40, you'd end up at the same spot that I did. So what's so great about radicals is that whatever number's out here for your index, that's what kind of groupings I need to make inside. So I'm looking for a group of 4. So let's rewrite 80. So instead of saying 80, I'm going to say 2 to the 4th times 5. Because that's really what I have, right? 1, 2, 3, 4 2s and a 5. One last step and we are done. When your index matches your exponent, they cancel each other out, and this base gets to come outside. So I always like to underline what gets to come outside. So a 2 gets to come outside. I'm going to circle what has to stay inside. The 5 has to stay inside because did it have a 4th power? No. Only if your exponent matches your index, that's the only time that base gets to come outside. So my final answer is going to be 2, 4th root of 5. And I know it's been a really long time since we've done these. So when we're given only numbers in our problem, you have to think to yourself, I have to make a factor tree and work this out. Do I really want to work out 80 to the 3rd power? No, there has to be an easier way. So we reduced first. Then I did my factor tree for 80. Since it's asking me the 4th root, I needed things in groups of 4. Anything that's a group of 4 gets to come outside. Anything that is not a group of 4 stays inside. I'm filling your brain with lots of good info. I see your brain's like turning in front of me. Okay, so here's why you need exponential notation. You ready? I'm going to give you a quick little history lesson here. So let's read about this. It says, the legend goes that the tradition of serving, I don't even know how to say that. I should have asked Mr. Bremer. I'll just say Pal Siam, to visiting pilgrims started after a game of chess between the local king and the Lord Krishna himself. The king was a big chess enthusiast and had the habit of challenging wise visitors to a game of chess. One day, a traveling sage was challenged by the king. To motivate his opponent, the king offered any reward that the sage could name if he won. So the sage modestly asked for a few grains of rice in the following manner. So this is only if he won, right? This is what he's asking for if he won. The king was to put a single grain of rice on the first chess square and double it for each remaining chess square. So on square number 1 would be 1 grain of rice. Square number 2 would be 2 grains of rice. Square number 3 would be 4 grains of rice, right? It would keep doubling, so on and so forth. So following the exponential growth of the rice, the king quickly realized that he wasn't actually able to pay off his promise, because it seems like if there's 64 squares, right? Think about what the answer would be on that 64th square. It doesn't seem like it would be that big of a number. But exponential graphs are really growing crazy, crazy, higher, 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 because if each time you're doubling, you can kind of see up here, by just the last square you're at 128, and then the very next time down you're at 32,000, then 8 million. See, I mean, it's getting huge fast. So by the time you're on the 64th square, it would have been 18 billion grains of rice. So he really tricked the king, asking for something small, but when you use exponential notation, it's actually increasing like a crazy huge amount of a number. So kind of interesting. So it's part of the history books that even to this day, they are still saying that people are paying off his debt, because when they go and they make like an offering at the temple, they're still paying with rice just to pay off this debt. So anyway, it's just an old saying, gets tied into the history books, but that's why. So exponential notation increases really, really rapidly. We're going to do a couple things with the iPads today if you're here in person with me. If you are at home, I'd like you to go to desmos.com. I'll put it on the slide right here. It's www.desmos.com. So at home, can you guys pull up that website? And if you're in here in person, can you guys grab your iPad? And we'll start in just a moment. Okay, for those of you guys watching at home, can you let me know when you have desmos.com pulled up, please? Okay, great. So I'm going to try and share my desktop here. That way we can all see the same thing. Okay, so here we go. If you're at home, can you give me a smiley face if you can see my calculator up on your screen? Awesome. Okay, so we're going to try the first one. We're going to use our graphing calculator to investigate. So our first one we're going to type in is y equals 2 to the x power. So when we're using Desmos, you don't have to put the y equals portion, So what you guys are going to type in is everybody put a 2. And then do you guys see how the x is in the exponent now? It's not like 2x, it's 2 raised to the x. So on your Desmos.com, we're going to pick the button that says a raised to the b power. When you click that, it moves your cursor to the exponent area. And now you guys will put x. How do we do? Does yours match mine? Yes, no, maybe so? Okay, so remember, it's increasing super duper duper fast. This would be the case of the rice, where it's doubling. That's what the 2 to the x means. Every single square is going to be doubling. So look how fast it rises. If you want to push your minus sign, it will zoom out so it kind of shows you your graph a little bit better. So you can see it on a bigger scale here. So like if you're talking at a value of 1, it's not very high. But a value of 5, look, it like jumps way, way up, like past 40. So it's just increasing really, really steeply. Now let's go down to the number 2. Leave 2x, 2 to the x in there, and let's try 3 to the x. So let's type 3, your a to the b power with your x. And notice what Desmos does for you is next to the formula, it shows you what color. It's graphing your line. So my 2 to the x is red, my 3 to the x is blue. So what can you guys tell me about these lines? As my number increases, what's happening to your graph? It's getting what? Compare the blue one to the red one. So the blue one is getting, what do we say? It's increasing faster. It's steeper. Good job. Okay, let's compare this. Let's go to number 3 now. Let's try 1,000 to the x. What about that one? What about your green one? So it's pretty much going straight up. Because how many times is this increasing on every square? 1,000 times what you started with. So if you start with 1 grain of rice, what's the next square going to be? 1 times 1,000, 1,000. What's the second square going to be? 1,000 times 1,000. Do you see what I mean? It's increasing super duper duper fast. Good job. So let's erase number 3 and number 2. And let's try some decimals now. We can erase 2 to the x too. Let's start over. So we're going to move to our middle line on our notes. Let's try 1.9 to the x power. And let's compare that to 1 to the x power. What do you guys see about your blue line? Goes straight across. Why do we think it goes straight across if it's 1 to the x? Think about if your x is a 5. What's 1 to the 5th power? 1. What would 1 to the 20th power be? 1. So no matter what value you pick, even if you pick negative, you're still going to get 1. No matter what value you pick, if I pick 20, I'm still going to get 1. So only when we have fractions, decimals, anything other than a 1, you're going to get your exponential graph. Let's do a third graph. Let's try 1.1 to the x. Okay, so this one would not be as steep, right? Your green one's not quite as steep. Let's think why not. Compare it to our red one. So our red is almost 2. You're almost doubling each time. Our green one is much closer to 1. So you're not quite doing 1 times the number each time. So the higher the number, what can we say? The higher the number, the steeper the line. Yep, the higher the number, the steeper the line. So what do you think will happen with the fraction? Would a fraction be steep or not steep? The higher the number, the steeper the line.
How big the fraction, or how, like the first number.
Okay, so I'm hearing that it depends. So what I want you guys to do is, you see our third column, it has 0.9 to the x and 0.5 to the x. Can you please try both of those? These are from our notes. So I'm going to let you guys try both of those for just a moment. So 0.9 to the x power and 0.5 to the x power. Try both of those out and compare them. Okay. And please do not think that this website is cheating. It's not cheating. It is saving us time from making a table that we could make ourselves, which in Algebra 1 you had to do a lot of tables by yourself. Algebra 2 you graduated away from that to the point where we can use sites like this to help us explore really what's going on. Not cheating. Isn't it pretty user-friendly though? Like it's not hard to use, right? The website? It's pretty intuitive. So I have my 0.9 to the x and my 0.5 to the x. What do you guys notice about these lines compared to all the other lines we've done so far? They're slanting in the opposite direction. Good job. So as you're going from left to right, they are decreasing. See? So as we're going from left to right, they are decreasing. So just like you guys told me, they won't increase as fast. That's absolutely right, because actually if they're fractions, they are decreasing graphs. Okay, so at the bottom of this slide, let me go back to the PowerPoint for just a moment. How do I get out of screen sharing? I don't know. Okay, so I'll just talk you through it. At the bottom of the slide, there's a note that I want you to add some blanks in, because I put some blanks there. It says, by making x negative, we get a reflection. So reflection is what should be added to your first blank. We get a reflection about the x-axis. About the y-axis, sorry. As a result, exponential growth becomes exponential decay. So the first blank is reflection, and the second blank is exponential decay. Okay, turn the page. We're going to try a couple more. This time, if you notice, I am adding some values to the exponent. Sometimes I'm adding values to the end of the problem. So first let's do what we call my parent function, which is the basic version of the graph. So let's all graph 2 to the x. After my 2 to the x, let's graph 2 to the x plus 1. Now notice, the plus 1 is a big plus 1. If you're looking at your notes, here's how you do it on Desmos. See how right now my cursor is still blinking right next to the x? Everybody kind of with me? After you first add in the x for 2 to the x, your cursor is still blinking next to the x. That's still in the exponent area. I just want to add a regular plus 1. So you guys need to use your right arrow or tap. See how they have this right arrow right there? You could just use that right arrow. And now my cursor is next to my whole 2x, and it's going to let me add in a plus 1. I'm going to zoom back in because this is an important point here. There. So check out what happened. My red line is 2 to the x. My purple line is 2x plus 1. What do you see happening from my red line to my purple line? What do you think that plus 1 did to my problem? It shifted it up 1 on the y-axis. Good job. Just like what we learned previously, if I have an x squared plus 1 and I add 1 to it, it takes your parabola and it shifts your graph up 1. It's going to do the same thing with exponentials. How do you think it would be different if that plus 1 was in the exponent still? So we're going to try one more. Let's do this light blue one. We're going to do 2 to the x. This time leave your cursor in the exponent area and we're going to add 1. Oops, that didn't do that for me. You want to stay up there. X plus 1. Were you able to graph all 3? Did you figure out how to get your exponent to stay? No? Okay, I'll come by and help. Okay, so for right now, just take a peek if you're with me in person or if you're watching online and you couldn't get your calculator to go. I will definitely help you before we go though. Take a peek. So this first one, I have the 2 to the x plus the 1 on the outside. This one has x plus 1 all as the exponent. Do you see how my orange line looks totally different than my purple and my red line? So if I add 1 just to the very end, it's going to shift it up or down. If you're adding 1 inside, what do we think is happening there? Close, yep. So this, he said that we're adding it to the exponent, which is totally true. But there's actually a rule for it. So let's see. I don't know how to make it stop sharing my desktop. I should have figured that out before I'm trying to do this today. I'm like, how do I show you guys my PowerPoint again? I don't know. I guess I could just pull my PowerPoint up. Okay, I'll do a hack job. Hold on one second. Not quite what I had planned. So at the bottom of your slide, if you already have your slides open, I'm giving you some general rules about exponents down there. There we go. Okay, so if you're watching from home, I apologize that I couldn't get my desktop sharing to stop. So right here, we're going to fill in. Here would be your formula, y equals a times b to the x minus h plus k. So h is going to represent the horizontal shift. What does horizontal mean? Side to side. So in that last column that we did when we added 1, we were actually shifting my graph side to side 1. Interesting. When I add a number to the very end, what does that do to it? Shift it up and down like we were talking about, shifted my whole graph up 1. And if I add a number in the very front of my problem, that's what we're going to call the stretch or shrink factor. It's going to make it go really, really wide or really, really tall. So those 3 at the very end you have to fill in yourself. So horizontal shift, vertical shift, and then stretch or shrink factor. We've seen these A, H, and K over and over again in Algebra 2 when we were talking about absolute value graphs, parabolas. They're always the same. So the number at the very end is always up and down. The one inside the parentheses is always left or right. And the one out in front is always your stretch or your stretch or shrink. Okay, so for those people who are at home, to get credit for today's session, you're going to just take a really short quiz for me. This is practice for our state test that we have coming up. I'm going to put the link in the, oops, that didn't copy right. Oops. All right, so I'm putting that in the chat area, but that's wrong. So hang on 1 second. I don't know why that didn't copy. This is given to us by the Cal State as a way for you guys to practice for your state test. So if you're here in person and you want to practice, absolutely you can. You have the link, or we can copy it down for you, but it's not mandatory if you're here in person. So those of you watching at home, you'll take your test, and I want to know what your score was in the Dropbox for week 5, and that's how you'll earn credit for this week's session. So thanks so much for joining me at home. I did give you quite a few more graphing calculators problems to practice, so I highly recommend you do that just for fun and so you can see how changing A, H, and K changes your graph. So thanks guys at home. Have a great day.